There you go.
Hello, everyone. My name is Chen. I'm currently at the University of Michigan. Today, I'm going to talk about comparison of goodness fit assessment methods with C statistics in astronomy. Renee warned me not to prepare too many slides, so I have a very simple sketch of the talk. I'll begin with some motivations about a spectral model. This is more for statisticians, so why we got interested in this problem. And I will talk about the definitions of C statistics. And there are multiple definitions of the C statistics. And I want to clarify them. And then I'll talk about the hypothesis testing, which is about goodness of fit assessment using C statistics. And then talk about numerical performances. So in terms of spectral model, this is a typical spectral model given by Ni is the number of counts that you get from energy being I. And then theta is an unknown parameter, which could be multidimensional. And each of those Ni's are independently distributed as a Poisson distribution with the rate given by SI theta. So SI theta is a known function, but there are some complications with this calculation of this known function that I'll introduce in a bit. So typically in the astronomy community, the chi-square statistics has been used for performing model fitting and goodness of fit assessment. And the chi-squared can be defined as the squared difference between the observed counts and the Poisson rate divided by either the Poisson rate or the observed count. And we all know that if each of those Ni's are really big, then the chi-squared is actually a very good approximation. And large sample asymptotics can guarantee that for both model fitting and goodness of fit assessment, you're good to go. But then in the low count setting.
Jan, before you go on, that I have a question both for you and for Renee, the two parts. You know, we have these two, right? Asymptotically and the null, they're all chi-squares, but just theoretically speaking, Jan, which one tends to have better finite sample performance? And for Renee, the question is in the community or anybody else is there a preference to use one of and do people discuss the pros and cons of each of these two choices? It's just how do you normalize, whether you use N or using S?
Renee, do you want to go first?
Okay. So yes, actually, the Keith is on the line, so he's probably the best person to answer this. But
I don't mind interjecting one thing. The only thing that I do know on this is that if you use SI, I believe that that's what Wilkes called the modified chi-square, right? So this is the one that has the better theoretical properties, right? So basically, you use the same. Yeah, you can see my pointing here, but basically the one on the left. That is my understanding that that's what's referred to as the modified chi-square. But traditionally, the one that was proposed first was the one on the right by, I believe, Pearson and all the people who did early work on counting. Anyway, that's the only thing that I have.
We call the thing on the right as the data variance, right? So, sorry, Keith, go ahead.
Yeah, I'm just going to comment. My understanding is the one on the left is better to use, but there is a practical issue when you're trying to find the minimum. If you start the model off a long way away from its true parameter values, when you're dividing by the model itself, you can actually have a problem. So often I tell people, use the one on the right to start off with, and then when you get close, switch to the one on the left.
Jeffers.
Before, I have a quick question, going back even further to equation one. I work more in the time domain than in the spectral domain. Do I gather that everything you're about to say would apply as well when S represented the time dependence of the flux of the source, for example.
I think so. The only thing is that they need to be conditionally independent. So the observed counts needs conditioning on the SI theta, whatever model that you have for the SI theta. As long as you have conditional independence, yes.
Yeah, that's pretty common. That relates to the observational errors and uncertainties, which is problematic sometimes. And another issue there, though, is that typically in the time domain, what you observe or what you are analyzing is not just the raw counts, but typically the difference between the raw counts on source corrected for counts off source. In other words, it's
The background.
a relative measure subtracting the background. So you don't even have a Poisson distribution for that difference. Are you going to deal with any generalizations beyond the pure Poisson case in equation 1?
That's a very good point. So the way that I'm currently thinking about it is that I add that background rate to the Poisson rate directly instead of subtracting some background from the raw Poisson count. So if you think about one Poisson process describing the source information, one Poisson describing the background information, if you add them up, it's still Poisson. So right now we're looking at the additive version, which is the total count that you finally observe, which contains, so SI theta has some background in there already. It could be parameterized or it could be not parameterized.
Oh, that's very interesting. Are you going to talk about that at all later? Or?
For this talk, it was not something that I prepared, but we do have one small discussion in our paper, which I can share once we finish.
Anyway, I'm glad to hear that comment. I was afraid, I mean, my expectation was that statisticians would try to work out for example, the Erlang distribution treats the difference between Poisson variates and so on, and go down the rabbit hole of exact distributions. But astronomers are more interested in the practical things connected with the real data. It sounds like the approach you've adopted is more practical and aligned with what astronomers would like to use. So thanks very much.
Yeah, thank you. Because we do have astronomers working with us who are pushing.
Yes.
Well, I would say, Jeff, what's interesting is that we got into this line is because we see astronomer was pushing the exact, I think the article, and then we realized that's not exactly exact as we would call it, and so that's why we got into it. And so, but you're right. In the end, nothing's exact, right? The exact is always a theoretical kind of goal, which is useful. But the reason I'm asking this question is now this part. I first want to see what in the astronomy community. Do you have any good consensus? And complete with what Keith says. The fundamental issue is that there are two separate issues. One is which one the chi-square approximate better and the null, but that's only one part of considering. The other part of consideration is which one has more power. And this is where I think what Keith said, okay, you can have a really bad model. You can imagine multiply SI by some really large numbers. One is affected much less. The other, if certainly will be affected more. I want to ask Jan, from a purely theoretical perspective, like from what you have understand, is there two questions. One is in terms of these asymptotics, is there a result to show the first one and the null? These chi-square approximations has a high order accuracy, and second is what are the theoretical results on the power comparison, even asymptotic, asymptotic of power. So that's on the theoretical question. But then also, I guess you have done this numerical simulation. I don't know if you have done both. There's the questions empirically, which one is performing better for both the power and the level.
Yeah, honestly, based on what we already have, I don't really have answers to your question because we study the C statistics, which is on the log scale and the counts, not on this chi-square statistics. But intuitively, I would say the left-hand side has a smaller variance marginally, right? Because the left-hand side, if you calculate the variance, is the variance of Ni squared, sort of. But on the right-hand side is the variance of a ratio estimator. So I feel from the variance perspective, the left-hand side statistics has a smaller variance, right?
You're talking about end of the null.
Yeah.
Because left side, I can make the variance anything I want, right? Because if I have a terrible model.
Yeah, in terms of model misspecification, yes. But we don't really have any theory of showing how these two estimators compare. If that's of interest to the astronomy community or statistics, I think we can look at it. But right now we don't have anything off the shelf.
But am I correct that the C statistics is actually the chi-square, the left one, is the first order Taylor expansion of the C statistics, not the second one?
Yeah, I think so.
Okay.
The
So
C
that's already
function.
yeah,
The C function.
that's function. Yeah. Okay.
Yeah.
Okay.
So this is just a one motivation for us because we see that for the low count setting, there might be some issues with the chi-square statistics. They're still independent, but they're not chi-squared ones anymore. So that's where we got started. And then the actual spectral model can be quite complicated. It's typically an integration over an energy beam that has the RMF and the effective area, and some kind of model, spectral model F as a function of energy and theta in there. So in this particular work, we consider different kinds of spectral model, which are all parameterized. The only thing that I want to mention here is that in terms of evaluation of this SI theta, typically it involves a pretty big summation. So computationally, we care about the efficiency of the estimators. And also, one issue that we never tackle is that we cannot calculate the true SI theta. We can always calculate a numerical approximation of the SI theta, which we cannot control the precision because the energy beams are pre-specified by the RMF. So that's one complication of the problem. But given that we try to simplify our framework, saying that we're only interested in the goodness of fit assessment of something that's parameterized by theta, which is a finite summation. And we're interested in seeing whether this spectral model fits the data very well versus the alternative, which is each of the SI is a free parameter. So that's the mathematical setup that we'll be working on for the rest of the talk.
Yeah, just before you go on, sorry, I'm gonna just, because this is also for my understanding.
Yeah.
A few things to clarify is I know you wrote this E little bar, upper bar, I think these are the limits. The question I have is for everyone essentially is, are these considered to be complete data independent? Or these settings will vary, depends on what problem you're working on, or is there some, and the same question for the M. Is M is a predetermined and not fitted by the model? Oh, that's part of the fitting as well. Oh, that's just a number of beans.
Yeah.
Number of components, isn't it?
M is supposed to be the number of beams, right? So
the number of energy beams, because it's used to approximate this integral.
Right, but it has not been settled according sometime looking data, saying
They're
these
usually
data
set
looks
ahead of
right.
time. They're usually set ahead of time.
Which means
but-
that next time
but-
you repeat this thing, you'll be using the same M. There's very little data dependent.
Yeah, with the caveat that when people use chi-square statistics, they often rebin the data so that there are 25 counts per bin. And
That's a
so
problem.
you've just violated, that fixed, data independent binning.
Yeah.
Actually, can I ask a question about this equation 6? I mean, why do you say that SI equals FI? Yeah, I mean, FI is...
No, this is just a generic notation. Sorry about the notation. You can ignore this part. So SI is just some function of theta. And yeah, this is a terrible notation.
Oh, it's
so
a function of the... I see.
Yeah,
okay, it's this F is not the same as the F in 5. Okay.
Can you
Yes.
just tell us what some of the G's might be? I'm a
Oh,
little confused
so
by
the
this
G's are
statement.
actually just these terms. These so the Cij, you can think about it as the R, Ej, I, and A, Ej. And then the Gj is just the F of Ej theta, and F of theta can be a power law, it could be a this kind of observed thermal spectrum model. So we
Right.
consider the power law and log linear models in our paper.
Right. If you were trying to decide how many of those terms to include in 4 and 5, or like you were deciding if you wanted to add a spectral line, it would be yet another sum that G is the sum over things. So
Yeah.
G are a sum of things on the log scale already for your models here, but I guess
Yes.
we know which components are included in the model.
Yeah, so G itself could be a sum, but it's not a big sum because this M is typically big.
Yeah.
In terms of hundreds of thousands.
So the question, just to follow up on what the Herman said, that's what part of my worry, that Jan, do you see actually, technically speaking, at least, the asymptotics will be different if you say the M was chosen to ensure each being has a minimum number of count.
It will be different. I think it will be different.
Right. The question is, so to be realistic in terms of what astronomy does then is, do we know the impact? Because our theory has developed with M is fixed, right? Not data dependent.
No. So in our case, we don't merge the bins. We work with the raw bins. So if there's 1,000 bins with 500 being zero count, we just take them as part of our model because Poisson model can allow you to have zero count. So the benefit of working with the direct C statistics is that you don't have to rebin. If you want to rebin, you can use the chi-square statistics. Everything is an approximation.
Yeah.
I get that. So that's good. But the question then is the original bin really original? Is the original bin itself has some data dependence?
At least for the data that Max gave us, there are quite a few small count.
Yes, it's defined by the instrument.
Yeah, there's an intrinsic binning of the instrument that we have been telling astronomers to use for decades now. I don't know how much they listen to us.
Well, if we have a software, that's why I really want to get this paper out. If we can publish the software, people can begin using it. If you have a good documentation.
Question from Doc or comment?
Yeah, so this is more again just about the shall we put it naivety of us astronomers. Even in the sort of the low count case, when people are trying to do this with Poisson statistics rather than using like chi-squared, we will end up binning data so that there's at least one count in a bin. So even in the sort of the hey, we don't have to worry about binning stuff. We know the data can be biased if we have lots of zeros in it. So it's really complicated.
Yeah. So in that case, we probably work on the conditional distribution of Ni conditioning on Ni greater than 1.
Yes.
So that will involve the normalization constant, which is not too bad for Poisson, right?
Yeah. I think we probably should do that. Jeffrey,
I'd like to second the comment about binning, and it's actually even more complicated. Astronomers use all kinds of binning methods. For example, Bayesian blocks is a binning method, mostly in the time domain, but where the bins are not even equal and they're determined by the data, by the statistics of the data. And then another even more extreme situation I think we'll hear about in the second half is bin-free methods, where you don't even bother binning because you want to extract all the information in the individual events. And anyway, just to throw in the complication of the real world a little bit even more. Thanks.
Well, actually, Jeff, I was going to exactly suggest to Jan say, can we derive a version we can call bin-free methods? Because in theory, by doing all the conditioning, right? Condition on the mechanism, meaning actually it's not being free, it's actually being adjusted. Basically, whatever they do, if we use the conditional distribution according to the mechanism they adjusted, it still be valid. So it's
I think so. That would be really
complicated.
interesting.
how complicated it would be if we just have a mechanism on binning.
No, I think it's doable. Think about it. As I mentioned, the simplest example is that you conditioning on each of the ni greater than 1. So you divide your current likelihood by 1 minus exponential negative SI theta, which is a continuous function that all of the derivations should still go through with quite different formula.
Yeah.
And the only tricky situation is that if you want to decide on where you bin, where you rebin, as long as the binning scheme is pre-specified, I think we're good. But if you give them like a dynamic way of specifying where you rebin, that's like complicated. I want everything to be deterministic so that I can do conditioning. I'm not scared about conditional distribution because it's Poisson, right?
Yeah, I see. So that's actually interesting. That suggests there's a second paper, which is once you figure out the methods that can being adjusted, then you can talk about what is the optimal choice of being in terms of maximized power, for example.
Yeah,
if the methods
that actually will be really interesting from a statistical perspective, right? Because it's not going to be simple large sample asymptotics anymore.
Can I say a small comment about this binning? So every time we change the binning of a data set, it's usually based on, I mean, so it's usually only based on the structure of the data, not on the model. So are you suggesting, Shaoli, that we should consider rebinning based on the model?
No, I'm just saying, I mean, this is purely statistical thinking.
Completely
whatever
data-driven?
you do, whatever you do, if it's data dependent, it will change the distribution, right? Change your null distribution. So that's where it will change to a conditional distribution, conditioning on how you did the bin.
Right.
This is saying we're looking at the power among all those methods which you bin the exact same way, and that usually give you better power. Am I right? David, with the conditioning.
Yeah, I don't want to inject too much and take too much time, but don't forget that whenever you bin at all, no matter how you do it, you're discarding some information that's present in the raw data. So if you can avoid binning at all, for example, using a truly unbinned approach like the CHASC statistic, that's all to the good.
Well,
it must be that the power is, do you think that you would get more power by binning the data? Is that possible?
People say that, but I don't believe it. I think that's
I don't believe it either.
Well,
there is one case where you would where that could happen, even if your native binning is subject to systematics, and then you bin so that systematics gets subsumed within the binning.
Can I just add something here? I mean, with the question of binning, I mean the instrument response here matters, right? So the energy resolution that you have, so this R term here, this is finite. And this means like at some point, if you use smaller bins or even like this, you will not gain anything like from using smaller bins. So you can actually figure out like I guess the ideal binning just based on the instrument response that you have.
That's an interesting comment because there's no definition for ideal. What is the ideal binning? Like you need to have a loss function or you need to give
Yeah, ideal means is mostly from computational perspective, right? Because I mean the binned case, if you just choose very, very fine bins, goes into the limit of the unbinned case. But at that point you have to treat each event individually, and this is just a computational problem. Right? If you have like thousands or millions of events, then it's just much easier to have the bin case. But then indeed, I mean, if you have the bin case, then you might lose information because of the binning. But if you do it right, so you can like, I mean, the instrument has a finite resolution, and this means, and at that point, it's just Nyquist theory, right? So we have it's like an ideal or like, I don't know, you can choose the binning somehow like 5 times. I mean, what astronomers do like 5 times the sigma of the PSF, something for image data. And the same you can do for spectral data, right? If you know the instrument response, then you know like once you have 10 bins per, like, I don't know, your energy resolution, then you're fine.
Yeah, I see. That's a good point. So essentially you want to
So I want to mention that there is actually a really important statistical thinking here. There is a principle here, right? Which is to condition on the ancillary statistics. The idea here is the binning itself ancillary statistics? If it is, you should condition on that. And basically thinking about it now, if I just tell you the bins without telling you the counts, can by knowing the bin themselves already tell you something about the theta, right? Because the whole idea of conditional ancillary statistics is saying you make your inference as relevant as possible for the study you have. So particularly with binning, obviously is part of your study. Now you want to bin away, essentially don't discard information about a theta because of the binning. But if you can do the binning without touch the theta, then that you definitely should condition on. Right, that's the whole T statistics and all the stuff there. So the likelihood will show. So what I'm suggesting that a formal way of doing this to write down a mechanism about binning. Say we know what the binning is a function of the data. Write down the likelihood to see when the binning mechanism is ancillary statistics. It no longer depends on theta. Because clearly when you're trying to bin things, because some bin has has zero counts, that's actually definitely has information in it. Right, information about the theta, but otherwise, so I think in practice it'll be very hard to do exact ancillary. But I think the thinking here to guide, I think probably, everyone you're saying these intuitions are pretty much behind that kind of thinking. But statistically, there's a way to write down the likelihood. You just need to formally including the binning mechanism as part of the likelihood.
Can you give an example of an ancillary statistic? I'm not sure what, for example, what's the most common?
Yeah. Okay. Let me give you the following. Suppose you have a normal 0 and data. So suppose you're estimating the normal model, estimating the mean and the variance. Okay, so you have mu and the sigma square. Now there is a chi-square to estimate the sigma square, right? The sample variance. The sample variance itself does not. Its distribution, the chi-square distribution, does not depend on the mean. So for estimating mean, that's ancillary statistics. But it tells you a lot about how hard the problem is. So when you do the inference, when you do confidence interval, you want to include that part because in a particular data set that you have, the sample variance could be a lot smaller than the average ones. So anytime when we do T statistics, we're conditioning on saying, I'm only looking at all the data that have the same kind of z-score. So that actually gives you really more power. You're not worried about average over data is like very different as squares.
Okay, that helps a lot. Is another way of saying it in terms of the term sufficient statistic, that if what you're after is a sufficient statistic, then you don't have to worry about some of these nuances.
Well, what's interesting, the nuance is that ancillary statistics itself is a part of the sufficient statistics. When you're estimating the population mean, like in a normal case, right? The sufficient statistics is not just the average, is as average and the sample variance if you do not know what sigma is, right? So that's but it is formal definition is the ancillary statistics is a part of the sufficient statistics, but its own distribution, marginal distribution, is free from the parameter you care about. That's what they call the ancillary. But it tells you, the ancillary statistic typically tells you, it doesn't tell you directly about that parameter you're interested in, but it tells you how hard it is. It's a measurement, it's an indicator how hard the problem is. So for example, if you see many, many zeros, the problem is indicating to you the problem is not that easy. Or maybe actually the other way around. If you see many, many zeros, that's probably easy because it's all low count. But if you see where some high count and some low count, and that probably gets the problem become harder. And if you're binning it according to, if you're particularly doing strategic binning, that's even more worrisome. If you say somewhere are being like because there was zeros, other places are being, because they're not zeros. Now your binning strategy definitely depends on what the underlying truth you want to detect. In that case, you have to be really quite careful without taking that into account. You may lose quite a bit of information.
Yes. Okay. Great.
I kind of like to move on. Can we move on? Because there's a lot of value in this particular analysis with presupposed, predefined binning, because we can have zeros. It's okay. We don't have to bin to have one count in every bin or any of that stuff. So there's so we could really go over this and then try to figure out cases where we need to go back to examine our binning approach. and the methods that will have an effect later.
Exactly. In fact, as Herman well knows, the instrument gives you the natural binning, namely the ultimate timing resolution of the detector, bins the data in zeros and ones with millisecond or microsecond bins. And a nice way to derive the cache statistic is to take the limit of that as these natural bins go to zero. But anyway, I'd love to talk about empty bins more. Someone mentioned a bias connected with empty bins, but I know we don't have time to go into that. But I'd love to know what that's about. I'm not familiar with a bias due to empty bins, but.
Yeah, yes, we should move along because Yang only has 7 minutes left to cover 12 more slides.
Sorry, Yang. Go on. We'll give you more time.
That's what I expected. So next I'm going to quickly go through the C statistics. Hopefully many of you are already familiar with it. So the way that we are defining the C statistics is through the likelihood ratio statistics, and the null hypothesis that we make is the true model, which is the SI theta, and the alternative is the fully saturated model, where each of the SI is estimated to be Ni. So this is the C function as a function of theta, and then typically the C statistics in the literature is this C mean statistics, which is the minimizer of this C statistics, also equivalent to the maximum likelihood estimate plug-in version of this C statistics. So we're able to reduce the problem to the case where if across all of those energy bins, in general, we expect a large number of counts. That means in total. We don't care about whether you have zeros or not. They are scattered around a lot of ones. That's totally fine. Or if you have one energy bin that has a lot of observations, that's fine. So we're working on the situation where in total, as long as you have enough number of counts, and then we can reduce the problem to where for each of those bins, the Poisson rate is bounded from above and below, and then the number of bins goes to infinity. This just makes our derivation in terms of large sample asymptotics much simpler. So in terms of hypothesis testing, what we can show is that if you plug in the true value of theta in the C statistics function, and then the difference between that and the C mean statistics, which is the C statistics in the astronomy literature, they differ by a chi-squared statistics with the degree of freedom D, which is the dimensionality of the parameter space. So typically, people use these two interchangeably in the astronomy literature, and because of the Wilks theorem, which we claim that you cannot be using them the same way. So we want to derive the large sample asymptotics for this C mean instead of the large sample asymptotics for C true, which is what the majority of the literature has been based on. So that's one gap that I want to point out. So our major result is this. So under certain regularity conditions and under the null hypothesis, we do have asymptotic normality for the C mean statistics, but this is not computable. So this is just only of theoretical interest. And then we have another result which shows that there's still asymptotic normality of the C statistics, but with the adjusted mean and adjusted variance parameter. And this essentially, these two quantities are computable because those are based on plugged-in versions of the theta hat. And the other thing that I want to mention is that this is sigma, the variance parameter here is the marginal variance of the C statistics subtracted by a term that's of order n. So that means if we just use bootstrap procedure, parametric bootstrap to estimate the mean and variance functions, we cannot achieve asymptotic normality. And we also showed this in numerical experiments. So that's the value of this result. Then finally, the version that we want to propose is this computable version that conditioning on the maximum likelihood estimate of the parameters, what is the mean and what is the variance of the C statistics as the number of bins goes to infinity. And this is well justified based on large sample asymptotics, higher order expansions, and it has a normal distribution, so we can derive a really simple Z-test based on the formulas that we derive. And actually, these kind of new results are not completely new if we constrain ourselves to the Poisson-count log linear models, because this has been studied quite a lot in the generalized linear model literature before. But our result is general in the sense that we're not restricted to the log linear model. We can work with any kind of model, any kind of spectral model in practice. So given all of those results, we compare all kinds of.
Sorry, yeah, I do need to go back. I know but this is important to understand, at least for me, because there's a couple of things puzzled me.
Yes.
First, let me talk about the bootstrap one. I think I understand what you're saying, but you are basically saying the bootstrap, as if you run the regular bootstrap, that it's actually will fail. It's the variance estimator is going to be actually smaller than what the bootstrap will fail. Not because it doesn't have a limit in normal 0-1, but when you do bootstrap, you don't care about normal 0-1. You're saying the bootstrap fails because it doesn't do the variance estimator correctly.
Yeah,
too small.
Yeah.
Okay. So the failing part is not necessarily the normal 0-1s, but rather the variance will be too small.
It is the variance term.
Yeah. What's the intuition there? Why the bootstrap will fail? Well, the variance will be too small.
What is the intuition here?
I see the term. The C here. What is the C? The little c there. The Q term, right? You have the little c. Little c has
The
nothing to
C
do
is
with
the covariance of the C and the score.
Okay, so essentially it's because the correlation between the C and the score.
Yeah.
Well, if that's interesting, because if the score essentially should be that's a derivative score, so average score should be 0. So why
average should be 0, yes.
Right, but why should there be a correlation here? Oh, that's because the number of beings. That's because the number of parameter goes up with the number of step data size. That's the problem, right? Because usually this correlation is 0.
Yeah.
Like if you do the likelihood. Okay, so that's but wait, but the number of data points is fixed, right?
Parameters fixed.
Number of parameters fixed, right?
Number of unknown parameter is fixed. But here you have SI thetas. You have n of them.
Yeah.
So you're talking about the Poisson expectation. So f of theta, or whatever it was defined before, is a value of more values.
That's actually very interesting. So you're saying the number of parameters are fixed, otherwise nothing will work. But because I'm testing more and more functions, and these S themselves are unconstrained with each other. So there is a price being paid there.
Yeah, because they have too many degrees of freedom.
Well, that's actually very interesting because, okay, so no, but that's something actually I haven't thought about. These functions are all have the same argument, but there are many different versions of them. So, and they are deterministic functions, right?
These are deterministic functions, yes.
And we're assuming these functions are known.
These are known functions, yes.
But there's still a price you pay by looking at all sort of these different aspects, I guess. Why there's a correlation between the score and that's interesting. That's number one. Okay. Let me finish the other one, because this other one is I'm even more confused. You said the first 11 is not computable. I understand not computable because the expectation of variance, they depend on the truth
data. Yes.
Right. But you can plug in, right? But once you plug in, you have problems.
That's exactly the problem that we wanted to point out.
Yeah, okay.
They're deriving 12.
Yeah. But what I'm confused, I think I wrote to you, 13, when you condition on theta hat, not plug in, that conditional expectation in theory still depends on the truth. Unless it happens that because theta hat is kind of asymptotically sufficient, so the dependence in the high order term, is that what you're saying here? Why that thing is computable? That's part of
this thing is based on the plugged-in estimator.
You still wait, no. 13 is not based on plug-in estimator. 13 doing the actual conditioning calculation.
Yeah, it is the joint asymptotic normality of CN theta hat and theta hat.
Right. But that distribution still depends on the true theta.
No, this does not do. So all of the cumulants that's related to this calculation in the approximation have the theta hat in there. So that's the entire derivation procedure. The only thing that we need to derive is that you need to have everything expressed in terms of theta hat. So you need to expand.
Right. Okay.
Yeah.
But so that's the power of that asymptotic, is because in general, as you know, C theta hat a joint distribution, right?
Yeah,
it's
they
still
depend on true
depends on,
data. Yeah.
it depends on when you do the conditioning, there still be truth
They
there.
still, yeah. I
Right,
buy
but
that
you're-
argument, but
Yeah.
the key thing about our derivation and the reason why the final formulae are so complicated is because you need to expand everything around the theta hat at the end of the day.
Oh, you did the additional expansion, so you put
Yes.
the dependence.
Yeah.
Basically, you're saying asymptotically the key parts, if you do the exact conditional calculation, is still not computable. But
No, it's
to the
still not.
point, so what you write there, technically speaking, am I correct? The
It should be
expectation on
the
the numerator,
hat.
that part is actually not its expectation, but with the theta has theta hat in it. After conditioning, you have the theta equal to theta hat in it.
Yeah.
Okay.
Yeah.
Okay. I think we should make it very clear, because this is
Yeah,
kind
there
of
are many
stuff.
notations that are a bit confusing here.
No, these kind of things going to pick up a bias by statisticians tell you that, this is really confusing, because they confuse the hell out of me. Like, why did you suddenly become
Yeah.
computable?
So
You are
we
just
can put a
saying,
little hat on the expectation variance, right?
no, I can help you. There's a way to write it, but it's very important here, because you're saying that you can plug in the theta hat in the marginal mean. That will not work. The asymptotic will fail. But you can put the theta hat in the conditional mean, which will work, because you already conditioned on it.
No, that's not the magic. The magic is the higher order expansion that you replace all the theta stars by the theta hat, but then you catch the extra cumulants. That's a result of that approximation.
I do understand that. We should argue, but that's essence is that the plugging the theta hat in that conditional one will work, because the lower
Yeah.
orders will work. Okay, so that's what they mean by this is computable, this is not computable. Okay.
Yeah, exactly. Yeah, so the vanilla version is not computable just because, yeah, it is the true data dependent. But both these versions are actually computable. And these has a more complicated formula, and it turns out the performance are similar between the two computable versions that we have.
Yeah, but let me say one thing to all the astronomers, because this discussion might be completely confuse you, but this is actually very important to distinguish. I think what happened with 11, this was that 2017 paper. They claim they have done exact calculation by assuming the theta is known and do this calculation, and that because the theta function, the C function with theta choose or theta plugin, these two will have very different behaviors. So I think what the Yang did is the 13 is to correct that. So you can get approximate exact answer, but you have to do the conditional distribution. You have to condition on what the theta hat is. You cannot say condition on what the true theta. Let's plug in. Plugging doesn't work. The asymptotics will fail, because there's too much uncertainty in that estimation to destroy that asymptotics. But when you say, I already condition what the theta has is, there's still some residual dependence on the theta, but that residual dependence is much smaller and high order. Therefore, when it is asymptotics, it goes away. The expression looks much more horrendous, but it's all can be computed.
So for 11, is it possible to come up with an example where it actually fails?
Oh, this is easy to fail. This is easy to.
Okay.
Yeah, that's a good question. Yang, can we come up with a simple example? For example, the C function is relatively easy to show what the thing is and how the correct ones do much better.
Yeah, we can definitely show that in the simulation experiments, as long as I think in the relatively low count setting, definitely that will be true, because we did have some comparisons of the histograms under different kinds of algorithms that we can, but we don't put a version of the 11 in there, which I think is a good point. We should put 11. The
Right. Put 11
non-computable
with the
version.
theta plugin. So this is what the people would have done, right? That's what's the CHASC paper 28. That's what they've done. They find exact expression for the C condition given that theta is true. Then they plug in process, but then we can show why that one fails because you failed to take into account the estimation problem itself.
Yeah, yeah. Yeah, I think we can definitely show that because for simulation experiments, you can also plug in the truth.
Yeah. You can,
so that's what you can, yeah. So you can compare the two distributions, plugging in the truth versus plugging in the MLE and show the discrepancy between the two different distributions and see how the p-values change.
And incidentally, Yang, this is why, you know, that idea of doing some that proposal, you know, but I have another question. So 12, right? Could we look at 12 as you correct for a bias in the estimation of the mean, or am I misunderstanding that? So in other words, I look at 12 as something that you can calculate, right? Because the hat is on top of
12 is something that you can calculate, and it's trying to correct the 11. And the 13 is completely different. It's kind of motivated from a generalized linear regression paper where they say by conditioning, you have better power.
Oh, sure, right. So okay.
Okay, we are running out of time rapidly. So Yang, if you could you wrap up in like 5 minutes, if that's possible?
Yeah, I think in terms of numerical performance, we just showed that if you do higher order asymptotics as compared to Bootstrap, the time in terms of computational cost, you save a lot. And also in terms of accuracy, you do have a lot of gain. And then in the real data set that Max offered to us, we can actually show that the chi-square distribution, which is corresponding to our algorithm 1, gives a result that's completely different from all of the other algorithms that we consider. So I think numerically we just want to we used some simulation studies, but I think we should conduct more simulation studies as you guys are discussing. I think we need more numerical studies to support the theory for now. And then in terms of real data, it's actually a very small data set, so we probably need to demonstrate that even further.
Yeah, and you also have the magic of crossing the 5% significance, right?
Yeah.
It's by coincidence,
Yeah, but I think this is quite obvious because the others are,
just
yeah. So I guess we'll just stop here now, and then I'll probably come up with more numerical illustrations and examples for the theory for the paper based on the discussions.
Hey, thank you, Yang.
Yeah, thanks for the comments. I think they are really helpful. There's still some chat that I need to follow up with.
Yeah, I put in the a reference to the Castro and Blaker, which was about trying to find the optimal binning for those people who are interested in that aspect. And I think Doug put in another reference.
Yeah, and can I ask your asymptotics n? What is growing? Is it the number of things?
So what is growing is that the Poisson rate if you merge all of the bins together. So that's the only thing that goes to infinity.
Total, like you're making the source brighter.
Yes.
Okay, that's
in
right.
total, yes.
Total brightness, yeah, perfect.
Yeah, total brightness gets larger, which is a pretty mild assumption that I think.
Right, it seems like the right asymptotics. Right,
that's the only one, right? That's the only one to, I mean, otherwise there's no, but I think I see there's a question here about a profile likelihood. I think this is actually the right term, yeah. It's a case of you profile out the theta itself. That you profile the theta. I mean, I actually running into this problem for another study. It sounds weird, right? Because the theta itself is everything, but you profile out because you care about the C theta.
Yeah.
You profile out the theta itself. You worry about the So
you think there should be literature on profile likelihood that can help?
Yes, I can give that to you. I can give it to you. Yeah, I think that's probably where Peter they did all his work because they're the ones on all these you know, all these profiles stuff. Yeah, but that's a good term.
Yeah, but I just want to mention that numerically our algorithm actually works really well. So that's why I think the software definitely should be published. But we'll wrap up the theory part.
Well, that's what matters, right? If the numerical did not work well, who is going to pay attention to this? A lot more complicated. But conceptually, it's very simple. We're just deriving the distribution for power average calculation condition on all the data set that will be giving you exact the same you know, MLE theta, right? It's conditional on you don't average over all possible data sets under the null. You average over possible data sets, give you the same maximum likelihood estimate of theta.
Yeah, I think that's a good way of summarizing that.
That's a lot more relevant.
Conditioning.
That's a lot more relevant, and that's where the power comes in, because you don't need to worry about things like you have not, you know, there's some theta hat may be crazy, but the other asymptotics will have to include those as well.
Yeah, exactly. We should incorporate that discussion in the paper.
Yeah, we you know, I can help you. I mean, I think we should have really put in the abstract to emphasize this these complicated things. Everybody gets a head spin, literally, all the profile high order asymptotics, but that's all they were trying to do. They're trying to do a more relevant calculation in terms of what's the replication and which you should evaluate the performance.
I see. Yeah, now I see why you mentioned the paper is far from being finished, but we'll work on that.
Well, it's all presentation, but I got so confused about the plugin, but now I understand what's going on. I think that
we actually worked on that notation for quite a few iterations already, but still, yeah.
No, that I think we can explain to people, right? That's pretty easy to explain. Asymptotics is hard, a lot harder, but
there is already a lot of theory in that paper, if you ask me. But it's and really astronomers, I don't think that we ever consider using the minimum condition on data hat, right? So this is new to begin with. So you know, my brain and probably that of many other X-ray astronomers is kind of you know, slow to catch up, right? That's impressive that you've gone so far, and that all the numerical simulations prove your point. Yeah.
Okay. Right. So only about 15 minutes late. Max, would you like to get started on your presentation?
Yes, I will share my screen, and I will keep it simpler because, first of all, not being a statistician, right? I can't go into all the level of details. So let me see. You're looking at my screen. Let me find the proper. Yes. Can you see my screen here with?
We're seeing two pages.
Yes, I think that's the way I would like it, because font size is large and it's easy to read, and I may go back and forth. So so if you can see my pages here, and you can also see that there aren't that many slides to begin with. So this is a very practical problem that we all often have, okay? And it's summarized by this spectrum here.
Max, I think it would be better to change to one slide per screen, because the font is really hardly readable in the background.
It is pretty small.
Yes.
Oh, okay. So let me try and do it. Let me try and do it like this. Maybe is it better?
Yes.
Is this any better?
It's a little better.
Well, okay. So okay, I'll start then. Hopefully this is good enough. You can't see the font very well, huh? I'm sorry.
Now it's better. Thank you.
Oh, okay, great. So the topic here is systematic errors, right? And first of all, I think what do we mean usually by systematic errors is that typically this is a portion of an XMM spectrum. You probably can see that, you know, there are dips due to inefficiency in the responses, right? Can you see my my mouse, the arrow here when I point to you?
Yes.
Yeah.
Okay, right. And so often, for example, often we have a situation in which we have many parameters. This used to be this was a spline, by the way, fit, and for a spectrum with many degrees of freedom and with many with many free parameters. Okay, so sometimes we come across the problem that the C minimum. Okay, so practically the CHASC statistic for optimized through maximum likelihood comes out larger than what you would expect according to the theoretical distribution, although there are uncertainties as to what the theoretical distribution is. But, you know, for example, this is a case in which C minimum was of order 1800 for about 1400 data points. Okay, and so obviously we have a situation in which either we say that formally the model is not acceptable, so we should just get rid of it, right? Or maybe invoke like this deus ex machina called systematic errors, right? So what are systematic errors? So now, right? I don't think that there is an agreement as to what is meant by them. Okay, I wanted, you know, for my own edification, to go through a little bit of a review of what was said about systematic errors, and I found this quote by Jeffries, okay, that says, you know, systematic errors which appear in every observation and persist in the mean, right? This is something that often we attribute to miscalibrations, and this is actually I really enjoyed reading this paper by David, and having to do with reviews of many ways of taking care of systematic errors. Now, you know, before explaining to you the idea that I had, you know, that maybe you can give me comments or shoot it down if it seems like it doesn't make sense. But, you know, what do we do in the regression of data specifically? If we have Gaussian data, right? So we usually would say, well, why don't we stick in another term for the variance, right? And then we proceed business as usual with the maximum likelihood fitting using the chi-square statistic. Now I called it S because I don't want to call it with a Greek letter, but basically this is the same, I believe, as Yang was using. I think the one on the left, except that instead of using mu I here, there is an extra a term for the variance, right? And so this is how this is the basic idea with adding a systematic uncertainty when you have Gaussian data. Of course, we don't have Gaussian data. This is the whole point here, right? And so, right, we are constrained by the fact that the Poisson distribution has the same mean and variance, right? And what could we do here? Of course, there are many things that we could be doing, right? None of which, however, is particularly easy, and it's especially keeping in mind that, you know, many of us, you know, struggle with going beyond, you know, a simple Poisson distribution. But just to be clear, right, you could use effectively like a negative binomial regression of Poisson inverse Gaussian, which right, technically comes with the compounding of the Poisson, right, with other distributions. But let's say we don't want to go that route, okay, and instead, okay, we really want to stick as much as possible with using the type of Poisson regression that also Yang was talking about. And in particularly, in my mind, okay, so when taking into account the systematic errors, right, you know, sometimes if you want to use nuisance parameters, and, you know, correct me if I'm wrong, but you have to use ancillary observations that sometimes you may simply not have available for them. And also sometimes if you want to use Bayesian methods, you know, you have to do a numerical integration of over the prior distribution. And generally, I think that we want to keep a goodness of fit measure, right, of the type that, you know, Yang has been talking about. And but, you know, if you use Bayesian methods, often you end up having a relative goodness of fit between two models, whereas often it's convenient to have just an absolute, right, goodness of fit measure in the traditional statistical sense, like a p-value, right? And so, you know, I believe that there is actually a very simple method that has all this, you know, desirables, so to speak. Okay, and so so I, you know, thought of and a way that we can overcome this problem. Okay, and so let's talk a little bit. Let's talk a little bit about what this idea. This is incidentally something that I already proposed in a paper in the monthly notices, but it didn't have much of the statistics, and I think that I think that I'm in the process of making a little more statistically sound. Okay, and so the data model is the same one as we had so far, right? So we have n independent measurements, right? And mu I here is the parent mean of the Poisson distribution, which is parameterized to a deterministic function f, right? And theta, I think here I call it m free parameters for some reason. Yang was using d, but that's the same thing. Okay. So, and we perform the maximum likelihood estimate, business as usual, with the Poisson, basically log likelihood. That's another way of calling the the CHASC statistic. Now, after the maximum likelihood regression is done, right, we could treat the maximum likelihood estimate at each I, where I represents the datum, right, and represents the ith data point, right? Instead of considering simply the usual estimate mu I hat, we can treat it as a random variable itself. The mean of the random variable, well, is actually the maximum likelihood estimator. And now we are going to introduce an ad hoc parameter, which is the intrinsic model variance, right? And so what I mean by this is the following. Now, of course, you have to choose a distribution for this new random variable. Now, of course, the Gaussian might seem like a nice option, except for the part that it may lead to negative values which are not meaningful. So perhaps a better choice is the gamma, but that's a secondary detail. Okay. And so what do I mean? What do I mean by this? I think that what I mean by this is is represented here, right? Imagine having the black data points. You fit them with a model, and the model of here was a linear model. It is the blue line, and after the fit, you treat the model. You enforce at each data point a randomization, if you would, that randomization according to this random variable mi, okay? And the idea is that this is the kind of randomization which represents an intrinsic model variance that we can use to determine now the minimum statistics in the presence of systematic errors, okay? And so the point is, can we use this method here of introducing? I'm going to go backwards, okay, for a second. Can we use this method of introducing a random variable mi, okay, with mean equal to the best fit estimate and an ad hoc parameter that is the intrinsic variance to determine a new goodness of fit minimum, which I will be shortly calling minimum systematic, okay, that we can actually practically calculate, okay? So, by the lack of any questions, I really wonder whether, I'm making any sense here, okay? So,
Max, quick question.
Yes.
So you're sort of defining a systematic error as just something that causes an excess variance. I mean, there's also this definition of systematic errors where you see a shift, a bias in the estimates, right? So whereas this is strictly
extra variance, adding the variances, right? So in other words, from my naive standpoint, the naive standpoint that I take is this. I mean, I can't add an extra variance to the Poisson distribution because I can't, right? So I'm just going to add it to the model instead of adding it to the data, if this makes sense.
Can I jump in? I think you're talking about what they call over-dispersed Poisson model, right? We have models to do that.
Correct. Yes.
Okay.
But I'm not talking about, so I don't want to use an over-dispersed model. And then, for example, I don't want to be using like a negative binomial regression, okay? Which is a way to take into account over dispersion, right? Instead,
But
I want to.
Can I ask why not? I mean,
Right. Why not? Why not is because one is a little more complicated, but that's hardly a good reason. The real reason is that I want to use all the information that we have for the C minimum in terms of its asymptotic distribution, right? So this is, and I want to add an extra a contribution to that distribution so that I can practically do hypothesis testing, which is exactly what Yang has been talking about, right? So this is like trying to take all the work on the asymptotic distribution of C minimum and asking the additional question, is there a way that I can modify that in the presence of systematic errors? If that makes sense, Vinay.
So you're effectively trying to see if there is an additional component that is needed.
Correct, right? So in other words, right, we've been investing, we are investing actually a lot of efforts into understanding the distribution of C minimum, right? Which incidentally, right, C minimum is this formula where instead of mi you have mu I hat, right? So this is so now can we in cases in which there are relatively small systematic errors, by small I mean the value of the additional variance, which was here sigma square intrinsic. So sigma intrinsic divided by mu I hat needs to be a small number. Okay, so can we in those cases find a way to have a distribution for this C minimum statistics in the presence of systematic errors in such a way that is the sum of two components? X is the usual one. X is the part that Yang is studying. We studied in the past, but now finally, Yang is making contributions in terms of better theoretical understanding. Okay.
So let me jump inside this. I see what you're doing, but let me provide you a different angle to think about this problem. And here's what I'm worried about. I understand that you say, well, let's just directly, since we have a C minimum statistics, it looks like may have additional component. I want to do this added term on it. That's all fine. I understand that. But let's think about what does it really mean, right? Because the C minimum statistics was a likelihood ratio statistics. Okay.
Right.
So the question is, if you add this thing, is there an underlying likelihood model? Is there an actual model well corresponding to this? Right? If it does, you can go back to working with that one. You will say, okay, let's modify the original model, right? It will end up at the C minimum statistic is like this. Now, what the Vinay suggests, it's entirely possible that we can, and I think I'm quite sure we can actually do this, that you take the negative binomial model and you basically expand the likelihood ratio of negative binomial in terms of likelihood ratio of the Poisson, adding the term, like doing Taylor expansion, right? Because negative binomial, the limit is Poisson. Depends on how you rate every single limit. Poisson. Right. So so what you did may have a real justification instead of an ad hoc way to directly attack the likelihood ratio, which I see the simplicity of that. There may be underlying models. You go back to say, oh, this is effectively like as if you are assuming another model. What's the benefit of that? Number one, whatever you do here, if it does not correspond to an actual likelihood ratio, that means you're not really doing the most powerful thing. There'll be information gets lost. Now, I'm not saying that's a bad way because sometimes we trade the computation, deriving simplicity to make this thing happen, which is entirely fine. So what I'm saying is that if goes back and has a model corrected for it, we rather do that model because that actually you can check whether that model has more physics sense, right? But if it doesn't connect to it, then I'd be more worried because you're not doing the most efficient thing. So I was thinking about adding a more complex model to the data, to the likelihood, and then doing a Taylor expansion against the Poisson model and to see what the second term is. You can still use that second term for your Y purpose, but you have a lot stronger story to tell. You also understand what the physics is. So that would be my this is my suggestion.
Yeah, this is great, and I really appreciate that comment. And actually, you know, a tailored series is about to come up in the next page, because I had something similar in mind, but obviously not what you just said. Okay, and so let me nonetheless carry on, and I'm taking notes of all the comments. So basically, right. So yes, this is in fact a very much, I think I already used the word ad hoc, you know, a few times, simply because, you know, my goal here is simplicity, and perhaps, right, this might not be as efficient as other ways of doing it indeed, right? But, right, so my idea is then continues like this. So now this is the new goodness of fit statistic, right? Now, first of all, I claim that these two components, X and Y, are actually independent of one another, okay? And being independent of one another, then basically Y, which is the extra component, right? X is the usual, Y is the new component. This is actually defined in such a way, okay? And you know, and I try to give some justification as to why X and Y might be or should be independent, okay? And actually, you know, maybe I'll forward the draft of the paper with anybody interested, and you can see what you think there. And therefore, what do I do here then? What remains to be done here for this very simple model? Well, what remains to be done, if X and Y are independent of one another, and if Y is asymptotically normal, well, all we have to do is to find the mean and the variance of Y, the new additional component, right? So in that regard, that is really straightforward at this point. And right, doing a Taylor series expansion here, and retaining only terms up to quadratic, and in the paper I try to be a little more precise with my notation, but right here, this is what I'm going to write. And so why you can approximate it for relatively small value of Fi, which is the relative value of the intrinsic variance with respect to the mean, okay? And it's really fairly straightforward. I would say much easier, certainly, than, you know, the calculation that Yang has been doing with the cumulants for the conditional distribution. This is just basic probability here. So we can find actually values for the expectation and the variance, okay? Incidentally, you know, all the way to the fourth order moment that we need to take into account. And so I asked myself, well, you know, obviously any of this, there is absolutely no value if the numerical simulations cannot be validated by using these expressions. Okay, so I spent some time doing some of those numerical simulations. So, and let me show you some of them, okay, which hopefully clarify a little bit what I'm trying to do here. Okay. So, for example, this is a case of a simulation for 100 data points, okay, n is 100, and there is a 10% systematic error, okay. So in the large count limit, right, the expectation of X itself, which is the standard C minimum statistic, is in blue, and you can tell it's approximately 100, right, which is because we are in the regime where the CHASC statistic is the same distributed as a chi-square distribution, okay? And now the part that I found you know, pleasing to see is that when I do these numerical simulations of this method for systematic error, the additional component Y, which is reported here in it's either red or purple, actually follows, you know, within uncertainties due to the you know, Monte Carlo simulations to what I was expecting, okay? And so this is a situation basically in which we will be getting a minimum of about 200, which again, you know, we have a choice to discard because we say it's too large, or attribute to the presence of 10% systematic errors, which incidentally are quite large. It means every model value, you know, has an uncertainty that is distributed according to a Gaussian with 10% relative standard deviation. Okay. So basically, what is the distribution then of Z? Z is a C minimum systematic. Well, clearly in the large mean, the limit is the convolution of a normal and a chi-square distribution. Of course, the chi-square distribution is itself normal in the if n is a large number. Okay, so really, obviously, the convolution to normal remains the normal. But I also spent a little bit of time actually carrying out the actual convolution of a normal and not just chi-square, but even more generally gamma distribution, which obviously is, and so actually it turns out that there is an analytic expression for the convolution of a normal and a gamma distribution, which I hadn't found in the literature. But in practice, okay, the message here is relatively simple, that we can use this, and I'm about to wrap it up here, okay? You can use this model in a couple of ways. One, in which if you have, if you don't know what the value of the systematic errors are, well, you can actually estimate them from the data themselves and this model. For example, you can just choose to set the expectation of the minimum systematics to the sum of the expectations of the two components, and of course you obtain an estimate for the mean of the y component, which can immediately link to the f parameter. And just to give you an idea of how this might work in practice, the example that at the very beginning of the presentation was a case of, I think I said 1400, it was actually 1500 and counting independent data bins. The C minimum was yay large, okay? And if we use this method, it turns out that we have a good estimate of the level of systematic errors at the level of about 2%, which is actually, from a practical point of view, was very pleasing to see, because this is the type of systematic errors that we think we have in XMM data based on the knowledge of the instrument. And finally, so either you use this method, to estimate the systematic errors. Basically, you are assuming that the model is correct. So you can do hypothesis testing, or you can do hypothesis testing, and then right in the so you can now test the null hypothesis using, for example, in the extensive data limit, and as I said, large mean case, just set the normal distribution, but instead of just having n minus m and 2n minus m, you also add an extra component for the mean and an extra component for the variance. So the method becomes really trivial, just like you would be doing hypothesis testing with a chi-square distribution. There is nothing else. There is nothing else to this. So this is, my short idea, and I really leave it at this. And perhaps, I'm going to leave it at the page where I have the definition of the random variable mi, and yeah.
Oh, thanks, Max. That was very interesting. Questions? I have some, but I'll let someone else ask first. Herman.
Yeah, I'm wondering about correlations between the systematic errors between different bins of the data set. Because often we would see, let's say that you're systematically off by, say, 5% in one place, and it's and that's 2% in another place, and they go in the same direction. How would you?
Yeah, right. I mean, I see what you mean. Right here, in the simple version, right? Every bin, the data are independent, and so are the value of the intrinsic error. Now, of course, you can easily take into account the fact that, for example, certain data points have 2% uncertainty and certain at 3, 4, 5%, but there is no account at this point for possible correlation between, for example, adjacent data points, if that's what you're talking about, Herman.
Well, yeah, that you know, when an entire energy range, let's say, has the same offset, then, you know, all of these data points in a row, you know, are going to be systematically offset, and it's not random, the offsets between bins, because they're correlated, because they have because it's more like a factor that should be multiplied by the model, you know, multiplied into the model.
Right.
And we've been talking about this in our concordance, and previously we talked about this as a thing that one could do to like fit overall splines, let's say, which will enforce correlations in the systematic errors, because systematic errors are usually come up because there was something that was mismeasured somewhere.
Right.
And not because there's an extra noise term.
Well, I mean, I would look, and of course, this is a good point, right? I personally would look at it, certainly, right? Let's say you have an offset by, you know, 20 volts when you use your voltmeter, right? You correct for that. So in other words, you know, there is an actual bias that you should first correct, but then there is an additional variance left over by the time you make that correction. This would be my view of, you know, an additional error, okay? But I do see your point exactly, that, you know, so this would be simply whatever is left over after you take into account that bias. Yeah, but Jeff maybe has something else better to offer.
Yeah.
No, I had a completely different thing to bring up. So if you want to continue this, go ahead.
I'm just going to make a very quick comment. I think that you two, what you're thinking, can be connected here, because I think what you're doing, as I said, because you're working on the likelihood ratio directly, and I think whatever you added, they should be. Now I'm thinking about, they probably even have a 1-to-1, some kind of renormalizing. You will have a model. So anytime you have a model, you do likelihood ratio, you do the Taylor expansion, you have an additive noise. So you can see, maybe, you know, the question is whether, and the model base may give you a better way of thinking about, like, for example, how the correlation affects that second term. So it will be still, you can still do the additive thing, which I see the simplicity of that. That's easier to calculate. There's lots of other things. But in terms of getting better, you know, because you adding on directly the second term Taylor expansion, you may lose some intuitions. You work on the model side first, then you map to that. You still get what you want, and that term will have a very good you know, explanation. Very much like the chi-square itself, right, is a first order Taylor expansion on the, you know, on the C statistic. We have seen the C stat is, you know, is doing better. The other thing I want to make very question, you mentioned about Young's calculation takes more things. Your calculation can be also done on the conditional version if you want to, right? You will run into the same problem. So we can take your statistics again, doing the conditioning on the theta hat to get a better power if you want to go that route. That will be additional complications, but yeah. So that's
actually,
so that's,
I had a question that
is really for different purpose. Yeah.
I had a question that follows up on Shaoli's comment about the theta hat. So Max, I mean, you're doing, as I understand it, you're doing this in multiple stages, right? You're first doing the Seaman, and then you're calculating the addition.
Correct. So this is, you know, right. Correct.
So, but if you do that, how are you sure that your Seaman is actually the global Seaman? And does that mean that the Taylor expression is actually valid? Because if it's not going to be, strictly speaking, at the true maximum or minimum.
Right, that is correct. You know, in other words, the proper way of doing it is exactly that of using a physically, I guess, mathematically motivated model for the for yi, which is like an over-dispersed distribution. That is correct. So, so I take your point well, in the sense that, right, but I don't think I have an answer for that. Yeah.
Well, I mean, it would be a good approximation when if your f sub I is small, I suppose.
Well, I mean, but certainly it should at least be shown, right? And incidentally, right, in practice, you know, the type of F sub I that we have, you know, are really a few percent, 3, 4, 5%, and now I have many more plots in the draft in which I show that up to about 10%, this model basically recovers well the distribution for C minimum systematic, but above that, you know, this becomes a poor approximation. Okay, yeah. But
let
if
me
you
just
think,
jump in. Yeah, sorry to cut you, because if you look at what Yang has wrote, I think Yang already identified what your model is. Essentially, is the Poisson mean has the
in the
gamma
chat.
distribution.
Yeah.
In the chat. So I basically am saying there is a model you can work with. I mean, if Yang's right, I think it's right. So so your approximation actually is assuming a model. Is essentially the mean itself has a gamma distribution. That give you the over dispersion without changing the mean, right? Because the expectations still correctly do. So then you can work with that, and then you can derive the MLE there. So Vanessa is right, because the ML itself will change a bit. So I think this is all the things that will give you a very systematic way moving forward. You still do all the things, then you have lots of interpretation there.
yeah, great. Actually, I just now looking at the chat. So yes. I'll take these comments very seriously. This is great. Yeah.
Jeff, I think this is.
Yeah, I liked I think it was your very first slide where you showed some quotations that imply that different people have different understanding of what systematic errors are. And I think that just in a matter of terminology and communication, that's important. I tend to think of systematic errors in the category of unknowns. But I guess it makes sense to talk about systematic errors where you kind of know the form of the departure from the truth brought about by some assumed or known cause, but there's maybe some parameters in that form that you don't know, so that it's sort of partially known and partially unknown. Do I understand the gist of what you're discussing here? Is that latter case where you assume a form but need to find some unknown parameters?
I mean, I think so. Okay, so what I'm trying to, in other words, to recap, right? So I am making the assumption here that on average, okay, the model that we use, imagine a spline, imagine a APEC model, imagine power law model, is correct. Okay, so but let me see. I'm not sure.
Not to interrupt, go ahead. You also mentioned a little bit of, I guess, degeneracy with nuisance parameters. So can you clearly distinguish a nuisance parameter from an unknown parameter in a model for a systematic error? Are those equivalent, or are they different?
I think in my mind they are different. Like a nuisance parameter is could even be like a background that you right.
Yes.
Right. But here is more along the lines of there is really additional variance in the data. Okay, where does that additional variance come from? And this is where I speak technically only of variance and not of a mean offset, like Herman was talking about. I'm assuming that the mean offset has been corrected one way or another, except that in the process of making that correction, you added additional variance, right? And so I'm only interested in, sometimes I think of this like a black box. I don't even want to know where that extra variance comes from. I'm just going to try and model it and see how much of this extra variance we might possibly have, 2, 3, 4, 5%. So this is very, practical and definitely not physically motivated, but,
And so you're treating that variance as due to a random, sort of a hidden random process.
Right. I'm just taking, the approach, the opposite approach of what you would do, I suppose, with a like a nuisance parameter in which, oh, I have a nuisance parameter that I make some ancillary measurements on and I marginalize over it. I don't want to do any of that, okay? I mean, that's all nice and well. And if you know where the extra variance comes from, I think you should do it that way. This is just a way that, you know, kind of like after I've done all of that, I still have a little bit of extra variance. Let's quantify how much that is and call it a day. Just, I'm trying to, you know, just, yeah.
Okay,
I mean, let me.
it helps me understand the big picture. Thanks.
I think there is something quite interesting, Massimo, what you're doing, because what I see here is you are essentially in a statistical terms doing some kind of measurement error model, right? You're saying, you know, whatever you want to call it, you call it hidden noise or whatever. It's there are some errors. You hope that error itself does not affect that error process itself does not contain information about, you know, it's not driven by the seed itself. Otherwise, you will induce bias.
Very good. Yes, you said it right.
You don't want to induce that. You want to have another mechanism to say, oh, there is some additional, like this is almost like a data privacy. Like, you know, you have the data, and before you get the data, some additional noise gets added, whether multiple added or something of that nature. Now you want to find, I guess you have certain assumption to be able to aggregately identify that. So what I see, I mean, just think about statistical, and I was pushing you to think about from the modeling aspect from day one. But I also see another way of thinking about yours. You say, well, I don't know what the process is, okay? But I have, now I'm inventing something. I say, I'm just going to add a term to the original perfect likelihood ratio model itself, right? Okay.
Right.
Now, the flexibility you have there, you can argue, say, well, you know, it may or may not be actually correspond to actual model. But I know that if you have actual model, there will be the second term by the tail expansion, okay? So now we're saying, let me add in the second term. Now, this may actually corresponding to a class of models. They all will behave like this. So you get a little bit of robustness. You say, this is a kind of a ad hoc way of correcting errors, not driven by any particular model, but by driven maybe a class of models all behave like this. You can characterize what I'm saying mathematically. You can characterize what other model will all give you terms like this.
Oh, I see. Yes.
Okay. And that gives you that flexibility you want. So I don't care about this very detail. I want to capture something, just move on. I think that would be a strong theoretical argument. But I guess the fact that Yang can identify the model immediately means that your term is not that flexible enough yet, because she can see what the model that was. So if you really want to push that argument, you make that term even more flexible, but now it comes with expense, might be harder to compute. So in the end, it may not gain that much, but I think I can offer you a conceptual way to push this idea of adding error correction directly on the likelihood ratio, not on the model itself. But you need to figure out this corresponding thing.
I guess I'm missing the point why that is not just an extended random error in the observations that you didn't take into account in your simple error model, and you need a more complex error model when you analyze the data. How is that a systematic error as opposed to a different random error that you hadn't realized?
I fail to understand the difference between random and systematic errors. To me, they're all errors, right? They're all sigmas, they're all variances. And so in that regard, I agree with you, Jeff, right? You know, so I'm just taking the view here that for the Poisson regression, if I still want to stick to Poisson because let's say I do, okay, then I just cannot add the additional error to the Poisson. Well, I'm just going to do the next best thing, which is I'm going to stick it to the model.
There is a pretty fundamental difference, though, between errors that go away when you get more data and errors that don't.
Yes, exactly. And also errors that sort of go one way. They're sort of like biases. The term systematic refers to the fact that it sort of is a systematic in the sense that it always biases the answer in some way. And if you knew what it was, you could correct for it. I mean, that, you know.
Right. And this is what I was, you know, saying before, that, you know, I regard as that part having been taken care of already, meaning that, you know, this is just the additional variance or uncertainty upon doing a correction, which in mean it's accurate. if that makes sense. But
yeah, let me add another point. Sorry, I'm always making things more complicated, but here there is another distinction to be made. We typically think about systematic errors as things going to cause bias for our final estimate of the theta, right? And one kind of bias is never go away, even with the infinite amount of data, right? And we think about other kind of measurement errors is like y's plus minus something. It's going to be in the end, it will make our uncertainty larger, but it does not bias our estimator, right? So that's the truth we're thinking about. The complication here is that you can have these errors, they do not depend on the theta, but because the estimation method itself is nonlinear, like these errors that on the measurement, that they can actually causing bias in your estimator, right? Because it's nonlinear. You do not average your way, okay? And I mean, so it's more complicated than whether the mechanism itself depends on the theta or not. You can perfectly not depend on it. It's very much like you do regression y on x. If you just add a bunch of noise to x, or add a bunch of noise to y, has nothing to do with the beta. When you do the regression, the beta is going to be much smaller because the noise added. You will never get it right. Even the process itself has nothing to do with the regression line, right? So I think that's what I'm worried about, because this problem is fundamentally nonlinear, right? All the Poisson stuff. So I think it's important to be very clear about, are you thinking about a mechanism, which I guess, Massimiliano, your idea is, you're not worried about a mechanism which involves the theta. It's some other actual random process adding noise, but that still can create bias. And the question whether that can be captured by adding a term, adding a second term to the likelihood ratio without having that thing involving theta, I'm not entirely sure. That's why I would push you to think about what's equivalent to class model. Maybe you're making an assumption, maybe it's not. So just need to see the mathematics there.
Yes, thank you. And incidentally, I'll be more than happy to share, the write-up that I have, just to let you know in slightly more details what I have in mind. But yeah, thank you. Yeah.
I was just thinking about this a little bit just now, that it's as though you're adding a systematic error in each bin, but the systematic error in each bin follows a distribution.
Right.
Okay. Whereas the things that we've been talking about that produce bias are the same across quite a few bins, let's say.
Yeah.
Okay.
Yeah.
And so they're correlated in that sense. There's sort of now a gradation of models of how to imagine what systematic errors do that take you from one regime to the other regime. Essentially, it's the scale over which the errors, the systematic errors, the biases, you might say, in each individual bin, the scale over which they are related to each other.
Yeah, I see what you mean. So basically, right, think about here where I'm pointing with the arrow, right? So imagine that for that value of the x variable, you have like a Gaussian distribution, right? Which I probably could have drawn, right? So in this plot here, each one of these, blue, steps is independent of the previous. But if you have reasons to believe, for example, that maybe for a range of, let's say, 1 angstrom worth of data, right, any error might be correlated, then maybe we should effectively like rebin, so to speak, right? So we should do only one randomization over not just 1 by 1, but over 5 bins or 10 bins, if there is a reasons to believe that, or something more complex, I guess.
Yeah, I think, Herman, you made a great point. I think that's where again, go back to the physical model would be important, because once you have this edited term add-on as in a sum form, you kind of lose the insight. And also I got reminded, remember in Yang's talk, there's this mysterious term about the likelihood, the score, the correlation between score and the C, right? And I think that is actually would be when you have systematic errors even they are not theta dependent, but they depends on the Bing index. They can creating correlations, and that could be, yeah. I think that's probably. I mean,
Yeah.
I very much like your idea of having one term to capture to see what's the impact. But I guess we need to kind of now go back to really model this whole thing and then see how the correlations, how the other stuff simplifies when we don't assume they're across the Bings and what it impact on on the second term. Yeah, I think there's a systematic way to deal with the systematic issues. Yeah.
Right. No, I mean, you guys are giving me enough to work for the next 5 years. You know, I'm right. This is great to hear. Yeah.
All right. We are well past our closing time, so we should probably bring this bring the curtain down. Thank you for both speakers. This has been excellent session. We can probably keep talking about CSTAT for a whole day, if not for a whole week. And we'll probably have to do that at the next CHASC meeting or something.
We will come back.
We'll come back. Yes.
Profile likelihood too.
Profile likelihood.
Yeah, I'd be happy to talk about profile likelihood because that's the whole thing.
Yeah. Why do they call it profile and not silhouette likelihood?
Huh?
Never mind. It's a joke.
But if Xiaoli want to talk about profile likelihood, I think we would all enjoy that.
Yes.
Yeah, I can certainly. I mean, I've been working on those things, and there's a yes in the Monte Carlo. The profile likelihood is this mysterious thing. I'm more than happy to not next week. I have too many things to do.
Not next week.
But how about I work with Yang because we probably can just use this example to think about how to think about profile likelihood. Essentially, is a cheap way to get rid of a parameter, a nuisance parameter. But then, of course, that's cheap way also comes with the cheap consequences. So that's okay, great.
Okay.
I think this is actually really good. So Yang, you and I should meet, right?
I can make you host, Yang or Xiaoli, and then
you can make
continue.
me host.
Yeah,
And
I
then I
might want to
can
take
log
just a
out.
quick break. I haven't had lunch yet, so what time would be good? Well, we can email each other. I probably
Yeah,
what
but
time is now?
anytime before 4 because